All right, let's jump right into this explainer. Today, we're tackling what is literally one of the most frustrating bottlenecks in multi-tenant microservices, configuration management. I mean, if you've ever built a SaaS platform that actually scales, you absolutely know the headache of keeping track of tenant metadata, right? We're talking feature flags, API endpoints, payment preferences. It's a giant puzzle. Well, today we're unpacking a really brilliant architectural blueprint straight from AWS that hits the nail on the head and solves this exact headache.
Here's our roadmap for today. We're going to cover 1, the configuration scaling dilemma, 2, the tagged storage pattern, 3, routing with a strategy pattern, 4, bulletproof tenant isolation, and 5, zero downtime configuration updates. Let's get to it.
So, Section 1, the configuration scaling dilemma, specifically looking at stale caching versus polling. To really get why this architecture is such a game changer, we kind of have to sit with the pain for a second. Every backend engineer knows this agonizing choice. You either risk stale tenant data by caching it way too long, or you completely overwhelm your metadata service with just really aggressive, continuous polling. Think about it. If you cache tenant settings for, say, 10 minutes, a user might toggle a feature flag and see absolutely nothing change. Bam, support tickets. But if you try to fix that by polling the database every single second to keep things fresh, well, your database bills are going to skyrocket, and your performance will grind to a halt as soon as your tenant count hits the thousands. So, what does this all mean? How do we actually break this compromise? How do we get both real-time freshness and high performance without just shoving all our configs into one massive, unoptimized database? Which brings us to Section 2, the tagged storage pattern and intelligent routing. Enter the hero of our story. This tagged storage pattern is an architectural approach designed to eliminate this exact operational trauma. It's actually super clever. By simply tagging your keys with specific prefixes, like say tenant_config, the system can automatically and intelligently route your requests to the absolute best backend for that specific data. Instead of trying to build a bunch of different configuration services or compromising on a single database, this pattern acts as a smart router. It literally just looks at the name of what you're asking for and instantly knows exactly where it should live. As you'll see, this whole thing is built across 4 really distinct, interconnected microlayers. We start down at the storage layer, which uses a multi-backend strategy. Then we move up to a high-performance gRPC service layer that routes the traffic, an authentication layer using Amazon Cognito to secure the borders, and finally, an event-driven refresh layer to keep everything totally fresh. Moving right along to Section 3, routing with the strategy pattern to ensure optimal backend selection. Now, this is where we stop trying to force one single database to do literally everything. We're juxtaposing DynamoDB against the Systems Manager Parameter Store here because different configurations have vastly different access patterns. For example, DynamoDB is absolutely perfect for high-frequency tenant-specific data, giving you that blazing fast single-digit millisecond latency. Parameter Store, on the flip side, is your go-to for shared static parameters, things like database connection strings, because it lets you pull an entire hierarchical organization of settings in one bulk request. Think of the strategy pattern inside our Nest.js service like a super efficient traffic controller. It examines each incoming request and dynamically directs it to the optimal storage service without needing any messy, complex conditional logic. I mean, without this pattern, your codebase would just be an absolute nightmare of if-else statements. The strategy pattern completely isolates that routing logic. By mapping these specific key prefixes directly to their optimized storage backends, everything just flows. Your application sees a tenant_config request. Boom, it goes straight to DynamoDB. It sees param_config. It routes directly to the parameter store. It is clean, it's modular, and it scales effortlessly. Plus, you can easily add new options later, like an S3 bucket, without breaking your core logic. But wait, it gets better. This dual storage approach pairs up with a really smart multi-layer caching strategy. High-frequency configs get application-level caching with very short TTLs, while those shared parameters just sit quietly in memory until they're officially changed. By matching the cache behavior directly to the actual use case, you're replacing wasteful polling with event-driven invalidation. It dramatically reduces your database reads. All right, Section 4, bulletproof tenant isolation. Now we have to talk about security, specifically avoiding cross-tenant data leaks. The absolute golden rule of this architecture is right here. The system never accepts a tenant ID from request parameters. Period. If your app relies on a URL parameter that says, tenant ID equals 123 to fetch data, you are wide open. A bad actor could literally just change that number and suddenly access a completely different company's sensitive data. No way. So here's how we fix that. The tenant ID is extracted directly from a validated JSON web token. It's a really slick flow. The client authenticates and gets a JWT, passes it in the authorization header, and then our guard validates that signature against the Cognita JWKS. Then, and this is the crucial part, the system extracts the immutable custom tenant ID directly from the token itself. The access guard verifies it, and the service layer uses that validated ID for queries. Basically, the system completely ignores what the user asks for and only listens to what the authenticated token actually proves. And that extracted verified ID feeds straight into DynamoDB's composite keys. Your partition key is tenant hash followed by that tenant ID, and the sort key is the config type. This brilliantly co-locates the tenant data for super efficient queries, and it physically locks data access strictly to that specific tenant partition. Even if, heaven forbid, there was a bug in your application logic, the database query physically cannot reach across the partition boundary. You get multi-tenant isolation baked right into the data model itself. Okay, bringing it home with Section 5, Zero-Downtime Configuration Updates using an event-driven refresh. Let's be real, for SaaS applications serving customers 24/7, the old ways just don't cut it anymore. Forcing a service restart causes downtime and drops active user sessions. And those polling approaches, they just waste API calls and introduce really annoying sync delays. You can't drop connections just because someone in marketing updated a feature flag, and you definitely don't want to pay for millions of empty API calls asking, hey, did anything change yet? Here's the modern solution, an auto refresh flow using Amazon Event Bridge. When a configuration in the parameter store gets updated, Event Bridge instantly detects that change natively in AWS. That event then triggers a tiny, lightweight AWS Lambda function. And what does that Lambda do? It reaches out to your running services and updates the local cache in real time. It's just a beautiful, reactive flow. The takeaway here is just absolute efficiency. Zero downtime, no wasteful polling. Your app just happily hums along, serving data straight from memory with almost zero latency. Then, instantly and silently behind the scenes, the cache updates. Your users get real-time freshness, and you don't pay a single cent for polling. To sum it all up, this architecture is a total game changer. Intelligent storage routing totally avoids those nasty bottlenecks. The event-driven architecture literally eliminates cache staleness. You get infrastructure-level tenant isolation, ensuring top-tier security. And thanks to pay-per-request billing, your operational costs stay incredibly low. We've solved the cache versus polling dilemma, locked down security, and built a truly reactive system. Which leaves us with one vital question to consider for your own microservices. Is your configuration architecture actually built to scale efficiently, or are you just polling for problems? Think about how you could apply these layers to your own systems right now to make them faster, more secure, and way cheaper to operate. Thanks for joining me for this explainer. I really hope it sparks some awesome ideas for your next build.